Okay, hi again everyone. Professor Sebastian. We're working on our Calc 3 notes and we are on page, 41. And before I move on about finding the velocity vector, let me review really quickly what we talked about in the last video. So we're now working in cylindrical coordinates, right, which has components r, theta, and z. So r and theta come from the polar coordinates that are down in the xy plane, and then z is just up however far up the z-axis we go. So now when we're looking at the vector r, we're talking about r u sub r plus z times k, right? So that's because we want it in terms of the vectors u sub r, u sub theta, and k, which make another right-hand frame. Instead of using x, y, and z, we're using u sub r, u sub theta, and k. Instead of using I, j, and k, we're using u sub r, u sub theta, and k, which is another right-hand type of frame. So the vector r is r u sub r plus z k. Okay. We also showed really quickly that the derivative with respect to theta of u sub r is u sub theta, and the derivative with respect to theta of u sub theta is minus u sub r. And we're going to use this shorthand notation for the derivative with respect to t. So u sub r dot means the derivative with respect to t of u sub r, etc. So now if we want to find the velocity vector is dr dt, of course, just like it always is, which with our shorthand notation is r dot. So r, remember, is r u sub r plus zk. So we want the derivative with respect to t of that. So for r u sub r, I need to use the product rule. So it's r dot times u sub r plus r times u sub r dot. And then plus z dot, in other words, just the derivative of z with respect to t in the k direction. So r dot times u sub r, we'll leave that alone, plus r times, and I'm just rewriting this to so you can see what's going on with the manipulation here. That's the derivative with respect to t of u sub r plus z dot k. So I did nothing but rewrite this and this u sub r dot right here. So it's r dot u sub r plus r times, now I'm going to apply the chain rule right here. So I'm going to take the derivative with respect to theta of u sub r, multiply times d theta dt. And you can see that the differentials d theta would cancel, and I have the same thing. So I'm applying the chain rule. And then notice that this guy is the derivative with respect to u sub r of d theta is u theta, right? U sub theta. And d theta dt is just another way to write, this theta dot is just another way to write that. So the bottom line is that the velocity is r dot times u sub r. R dot is the derivative of r with respect to t, plus r times theta dot. Theta dot is the derivative of theta with respect to t, times the vector u sub theta, plus z dot in the k direction. So that's velocity if I'm looking at cylindrical coordinates. Acceleration, again, is the derivative of velocity with respect to t. So what I need to do is take the derivative of this guy. So I got to use a product rule here. So r double dot times u sub r plus r dot u sub r dot. That's the product rule in this guy. Then I got to use the product rule here, thinking of r times theta dot as one function. So I'm going to take the derivative of this guy first. Now if I take the derivative of this, I got to use the product rule for that. So it's r dot theta dot plus r theta double dot times u sub theta, and then leave this guy alone times the derivative of this guy with respect to t, so that's r theta dot u sub theta dot. And then plus the second derivative of z, so z dot. Remember, the dots are just the derivative with respect to t. Okay, so now I'm going to simplify this. So leaving this guy alone, here I'm rewriting this as the derivative with respect to t of u sub r, just so you can, I'm going to apply the chain rule again so you can see what's going on here. Here I'm leaving this alone and this alone, and here I'm going to leave this guy alone. But whenever I have a u sub r dot or u sub theta dot, I need to apply the chain rule. So this is just rewriting it right here, with respect to t of u sub theta. Again, leaving this one alone, no rewrite. So I'm interested in simplifying this guy with the chain rule and this guy with the chain rule. So this becomes the derivative with respect to theta of u sub r times d theta dt. So the d thetas could cancel these differentials, and you see how that's the same thing. Same right here. Applying the chain rule, this is the derivative with respect to theta of u sub theta times d theta dt. These d thetas could cancel the differentials, so you can see that's the same thing. But then we make use of the fact that the derivative with respect to theta of u sub r is u sub theta, and the derivative with respect to theta of u sub theta is minus u sub r. And then I just bring all the like components together. So here I have a u sub r, and here I have a u sub r. So that's r double dot from this guy, minus r theta dot and then squared. So theta dot squared, that's derivative of theta with respect to t and then square it. That's the scalar component of u sub r. And then the scalar component of u sub theta, I have an r dot theta dot. From here, I have another r dot theta dot, so I have two r dot theta dots times u sub theta. And then I have an r theta double dot, second derivative of theta with respect to t. And then I still have my z. So there's my acceleration. Guys, you never have to memorize these. I derived them. They'll be on your formula sheets if you need them. Okay.